All right. Hi again, everybody, and thanks for tuning in. This week, our seminar speaker is Dr. Anicia Arredondo, who is currently a postdoctoral researcher working with the SOFIA Science Center at NASA Ames. Dr. Arredondo is a planetary astronomer, at least I think I would consider you a planetary astronomer, whose research mainly focuses on studying the physical and chemical characteristics of near-Earth asteroids and other small planetary bodies using telescope-based spectroscopic data. They received a bachelor's in astrophysics from Wellesley College and a PhD in physics from the University of Central Florida. And like I said, recently they just started their position at Ames working on the SOFIA telescope to map water and other volatiles on the moon. And so thanks again for taking the time to chat with us. Take it away. Thank you again.
Yeah, thank you. That's probably the best introduction I've ever had before. So thank you for that. Um, yeah, so I am not a moon scientist, just so we're all very clear. So if I do say anything, that an actual moon scientist thinks like that's completely wrong, please tell me because I've only been studying the moon for 6 months. With that in mind, let's get started. Uh, okay. So let me start by saying that water is the most precious resource in space. It can be used for fuel. It can be used as a shield for radiation. It can be used for life support, amongst a lot of other things. I'm sure a lot of you have heard of NASA's Artemis program. They're going to send humans back to the moon, including the first woman and the first person of color. The first step towards the Artemis program is this guy right here, the Viper rover. Viper is a resource mapping rover that's going to go to the moon and show where the moon's water ice is most likely to be found and easiest to access. That's going to tell them, NASA, where Artemis should land and, what the best place for human inhabitation will be. Viper is going to land in a crater near the South Pole. That's where water ice is frozen into cold traps created by permanently shadowed regions. And yeah, so the reason we care so much is because eventually this is going to help us get to Mars and to beyond, because we need a lunar outpost in space, and to do that we need water. So we need to know where the water on the moon is. So way back when, in the days of Apollo, it was thought that the lunar surface was completely dry. All the Apollo samples that came back, they looked, there was no water, moon's dry. Okay. However, recent studies have shown that that's not the case at all. 3 different spacecraft, Chandrayaan, Deep Impact, and Cassini, have all reported the detection of the 3 micron absorption band, which is in this left plot. That's from Deep Impact. 3 micron band is due to the presence of either hydroxyl or possibly molecular water, OH and H2O. You can see in the left image there's a clear absorption band around 3 microns in all 5 of these spectra that they're presenting. The plot at the right shows a map made with M cubed from Chandrayaan of the strength of the 3 micron feature overlaid on a map of the moon, which shows that there's this trend of more water towards the poles, which is kind of what we expected because of those cold traps that I mentioned. So this is the reason that Artemis and other countries' programs are so focused on the polar regions, is because maps like this have showed, hey, there's a lot of some type of O and some type of H mixed together towards the poles. Let's go there. And you can also see on that map that the Apollo landing sites are marked with yellow dots, and you can see why all of those samples returned were dry, because they're in the dry part. So that's kind of cool. So great, we know that there's a 3 micron absorption and it's widespread on the moon. Cool. The problem is that this absorption feature can be formed by either OH or H2O. And there's no way that the 3 micron feature can distinguish between those 2 different things. So I haven't taken chemistry since 10th grade, but let me try to explain this. The 3 micron band is created from the symmetric stretching and the asymmetric stretching of a bond of O and H. And so that can be H2O has bonds of O and H, and OH also has bonds of O and H. So they kind of mimic each other. And so, yeah, all the spacecraft who have found these 3 micron features haven't been able to distinguish between water and hydroxyl. And so we need a new thing to determine which is which. But thankfully, there's one more vibrational mode of water, which is the rightmost molecule that's bending. And OH can't bend because it's only 2 things, and that's just spinning around. So that vibrational mode has a distinct feature at 6 microns, which is strictly due to water. So hooray, we've solved the mystery. Let's just go look for the 6 micron feature. No, it's actually way harder than you think. I'm sure a lot of you have taken some sort of astronomy optical class, and you know that the atmosphere gets in the way of a lot of astronomy. This shows the opacity of the atmosphere for different wavelengths of the electromagnetic spectrum. And you can see that while we do have a very nice little window in the visible and a giant beautiful window in radio wavelengths, most of the other wavelengths are completely opaque or they look like garbage. 6 micron is pretty much smack in the middle of the mid-infrared, which is, I don't know where my mouse is, here-ish. So it's not as bad, but it's definitely not good. So this is the whole reason that we, as a human society, decided to put telescopes in space. And that's, you may say, well, we just launched a pretty big telescope into space, and that it definitely is for mid-infrared, and we definitely can detect 6 micron features with it. And that's true, but Webb is extremely limited in the fact that it can't look at bright things, and the moon is very, very bright. So that's completely out of the question. If we proposed that, we'd saturate the detector and they would never let us propose again. So yeah, the other option to observe this feature would be to rally a bunch of lunar scientists and create a new moon mission and make sure that that mission has a 6 micron detectable spectrometer on it. That sounds also very, very hard. So what are we left with? How do we observe this feature? Answer is SOFIA. SOFIA is the Stratospheric Observatory for Infrared Science, Astronomy. AKA it's a 2-meter telescope that NASA put in the back of an airplane. And it flies around, 40,000 to 46,000 feet. So it actually flies above 99.9% of all of the water vapor in the atmosphere. And this is fantastic because it means that we can observe the infrared without having to build a space mission. So it's by far the cheaper option of the two. This image here shows all of the wavelengths covered by the different instruments of SOFIA, and also Webb and ALMA are on it. And you can see that SOFIA has 2 instruments that are capable of observing at 6 microns. So not only can it do it, but we have our choice of resolving power. So that's awesome. Solve the mystery. So, in 2018, there was a pilot test to observe a crater near the South Pole, Clavius crater, which is on the map on the left, to see if SOFIA could detect this 6 micron feature. The left map shows that's the length of the slit, those lines, over the Clavius crater. And we obtained a total of 6 frames, and the results are shown in the rightmost plot. That is the normalized emission around 6 micron. And you can see that there is a feature there. in all 6 of the frames. So SOFIA can detect this. The thing is, if you look at the y-axis, you can see that this feature is on the order of 1%, 3% of the total. So it's a tiny, 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 tiny amount of water. Based on these data, we estimated abundances of water in this region to be about 100 to 400 micrograms per gram. And for those of you who do not think in terms of micrograms per gram, it's about 100 times less, 1/100th the amount of water in the Sahara Desert. So it's not a lot of water, but it is definitely water. And so the relative scarcity of the water here shows the importance of knowing where it is and how much it is before we go and spend billions of dollars on a space program to land there. So once it was proven that SOFIA was capable of detecting the 6 micron feature, we wanted to start making maps. Because like I said, we don't want to waste money going there if we get there and there's nothing. So we chose another South Pole crater. This one's called Moritis, shown in the map on the left. It's near Clavius, a little more farther south. We observed 95 frames this time, so that's about 15 times the amount from the first test. And then to give you an example of what we were expecting, here is the M-cubed map again with Clavius and Moritis circled. Moritis is a little bit more far south, but because of the length of the slit and the orientation of the slit, we were kind of expecting the exact same thing as what we saw in Clavius. And then the other circle there is this Mare reference region. And so the Mare are the dark parts of the moon. They're expected to be dry because they're basaltic deposits. And yeah, you can see that in the M-cube data, it's dry there too. So we actually use the Mare kind of like a flat field. That's why we call it a reference image. We can divide our Moritis data by the Mare data, and that can isolate the differences between them, which in this case, we're hoping is water ice and a 6 micron feature. So that's very important. The result is that we found that the forecast instrument, the instrument that we used, can indeed be used as an imaging spectrometer to make maps of water on the moon. This image on the right shows a sample of the continuum removed spectra, and you can see that there's a 6 micron feature in all of them, about the same peak height as the Clavius data in 2018. We estimate the peak height by fitting a Gaussian, which is what that red line is. And then there's an empirical relationship between water abundance and peak height based on spectra of water-bearing mid-ocean ridge basalt glass. And so we use that relationship to translate peak height to abundance. So it's pretty linear where a greater peak height correlates to more abundance. So based off of these data, we found a water abundance of about 200 micrograms per gram, which is right in the middle of the range that we found in 2018 in Clavius. And this left map's really cool. It's an orthographic projection of the peak height. And you can see that the brighter is more. So the peak height actually increases as latitude increases. So we can see that there's more towards the pole. So that's really cool. Yeah, so we also found that in our data, flux increases with decreasing latitude, whereas what I just said, the peak height follows the opposite trend. So the left plot kind of shows the inverse relationship between peak height and flux. This indicates a control by either temperature or latitude, but latitude really is average temperature or maximum temperature. So it's either diurnal temperature or average temperature is causing this. And that agrees with some of the trends observed by those 3 spacecraft that we saw earlier. The right plot shows bandwidth versus center for this data set. And then also it has the 2018 data on there, the mid-ocean ridge basalt in blue, and a couple of hydrated meteorites in black. And they all agree pretty well. And then we also derived temperatures from our radiant spectra, just with black body laws. And we found temperatures that are consistent with measurements that were made at the same latitude and the same time of day by the Lunar Reconnaissance Orbiter Diviner Radiometer. So all of our data match pretty well with the data we already have. We're on the right track. The detected water molecules that we found could be located in 3 different reservoirs. Where the water is located can give you evidence to where the water originated, and therefore what source of water dominates on the moon. So the first reservoir is on silicate surfaces. So what happens is micrometeorites or solar wind, that's space weathering, it will add hydrogen to the surface of the moon. Solar wind adds hydrogen to the surface of the moon, which makes hydroxyl. And then at typical daytime lunar temperatures, around 300 something K, it's hot enough that the hydroxyl can be synthesized to form water. And if this is the case, if this is how the water is coming about, we would expect variations with the lunar time of day, because the molecules would hop ballistically around the surface every time they got heated. And so if we see a variation with time of day, then that's the reservoir. The second option is inside of impact glasses, glass made from impacts. This also has 2 originating sources, either pre-existing hydroxyl already on the surface, or impactor water that was on the impactor before it impacted. When an impact happens, the amount of heat is such that it can either heat the hydroxyl to make water, which would then be incorporated into the glass formed by the impact, or it could vaporize the water inside the impactor and again put it into the glass. And so, yes. And so that's option number 2. If we see this, impactors don't have a preferred place to hit, and so if it's micrometeorites, we would not expect variation with latitude or time of day or anything. But if it was pre-existing hydroxyl, which would have come from solar wind, then we would expect that the intensity would decrease with the decrease from the equator, because that's how the solar wind intensity has been mapped. And so there would be a variation with latitude. The third reservoir is water that is indigenous to the moon. So inside of water can reside in igneous rocks or volcanic deposits. It's water that was incorporated from the molten interior of the past moon. To find this, we would need to observe geologically significant places where molten material from the mantle has come up to the surface. So things like crater peaks or pyroclastic flows. If we see water there, then that's probably what it is. Based on our data, we believe that option 2 is the most likely. And that's because for option number 1, as the water molecules are hopping ballistically with time of day, they have to pass through the exosphere. And the LADI measurements of the exospheric water are some amount, and based on what we measured on the surface, the amount in the exosphere would be much higher than that if it was all on the silicates on surfaces. And so because of that, we don't really think that number one is the main source. And then number three, it's not a lot of the moon is those kinds of surfaces, those special molten lava at the surface places. And so it's just not super likely that all of the water is there. And from our data, we did see kind of a trend towards the higher latitudes. And so that, for that reason, we think that number two is the most likely. We have quite a few telescope nights lined up to further test these theories. I think we have 7 more nights in May and then probably another 2 weeks later on in the year. So this kind of shows an example of what we're trying to get at. So by observing the point marked by these are moon pictures. The colors are temperature contours of the sunlit side of the moon. Purple is hottest and red is coolest. And you can see as the moon phase changes, the temperature at a specific point changes. So if we observe the point marked by the red star on both of these nights, we can test if the water is temperature dependent, because on night 1 it's in the green contour, it's cooler, and on night 2 it's in the purple contour, which is warmer. And so that's going to, a variation with the time of day would suggest that the water is being adsorbed on silicate surfaces. In the same way, we can test the latitude dependence of water by observing a few spots along the same temperature contour. So that's marked by the white X in the left plot, the white X's. They're all in the green contour, they're all the same temperature, so temperature is a control, and by changing the latitude, if we see a change with, in abundance with latitude, then that could point towards origins of solar wind implantation. If we see no changes at all, then that could be origins of micrometeorite implantation. And then we can also observe specific geologic locations, such as the crater peak that I marked with a yellow diamond. And that's looking for the indigenous water on the moon that comes up from the mantle material. So we have a lot of very interesting experiments coming up, and hopefully we'll be able to say, where the water came from, how much there is, if it's moving or not. We're also planning on making maps of very interesting regions on the moon. For example, the Viper landing site. This image on the left is a flux map that we made based on our observations around the Nobel crater, which is where Viper is landing. Preliminary, it's not calibrated right yet, but it's very exciting. You can see that the flux corresponds with distinct features. You can make out the Moritis crater and a few other craters. I put the picture on the right to show you kind of like what this map is showing, except flux, so it's cooler. So while the Viper site is going to obtain a lot of really high resolution data at the Nobel crater, these data that we got are going to be able to provide context for that and say, well, yeah, there's more here, but maybe you should go to the left and find more there. And so our hope is that these interesting large maps of the moon will be able to contribute to Artemis and any other country's future moon missions. And the main takeaway of this talk is that we're able to map the abundance of molecular water using the 6 micron band. which never been done before, completely new, awesome. SOFIA is the only observatory on Earth or in space that is able to make these measurements due to the fact that it can fly above most of the water in the atmosphere. With these data, we find that water is more abundant at high latitudes, which corresponds to lower temperatures. And based on our data, we think that the most likely host of this water is trapped inside of impact glasses. And this project is still developing. We have a lot of interesting stuff coming up, and I would love to hear any questions that you might have.
This is great.
Great. Yeah. Thank you so much, Dr. Arredondo, for that great talk. I'm going to stop the recording real quick.